The following video is on curve sketching. There's certain things that we can find mathematically that will allow us to draw the graph of a function. One of which is the x-intercepts. We all remember from pre-calculus finding x-intercepts. In order to do this, we set y equal to 0 and solve for x. We can also find y-intercepts by setting x equal to 0 and solving for y. We can evaluate the symmetry of a graph. There's two different types that we will be interested in. One is called y-axis symmetry, and one is called origin symmetry, or symmetry about the origin. Our graph will have y-axis symmetry if f of negative x equals f of x for all x. In other words, if I can fold my graph along the y-axis and have the two halves match up. My graph will have origin symmetry if f of negative x equals negative f of x for all x. In other words, if we can rotate the graph about a skewer along the line y equals x and get the same graph back. Some graphs will have periodicity. Usually these are trig functions. The period of the function sine of kt is 2 pi over k. The period of cosine of kt is 2 pi over k, and the period of tangent of kt is pi over k. We often want to look for discontinuities, and we've practiced this earlier in the semester. For discontinuities, look for points not in the domain and points where piecewise functions are being glued up. We also might want to find horizontal asymptotes, which remember we can do by taking the limit as x goes to either positive or negative infinity. We can find intervals of increase and decrease by evaluating the first derivative at each of the critical values and then testing the remaining values to see when the function is increasing or decreasing. We can then use the first derivative test to find the relative extrema. We then want to find the y values of each of these relative extrema so that we know how to plot these points. We can find the concavity of the function by taking the second derivative, finding the critical values, and then using the number line to test for concave up or concave down. Finally, we can find inflection points by first testing the concavity, finding the y values of the original function at the inflection points, and then plotting those points. So all of these things can be done without a calculator. This uses everything that we've done all semester, including limits, derivatives, continuity, and even some material from pre-calculus. So although there's nothing hard going on here, the hard thing for many students is just putting everything together into a single problem. Let's try an example. So let's look at f of x equals 2x to the 4 minus 8x squared minus 10. The x-intercepts of this function can be found by setting y equal to 0 and solving for x. If we do some simple algebra, we'll notice that x equals plus or minus the square root of 5, or x equals plus or minus the square root of negative 1. But we can't have plus or minus the square root of negative 1 because that's an imaginary number. So our x-intercepts are at plus or minus the square root of 5. For our y-intercept, we set x equal to 0 and solve for y, and we get negative 10. For the symmetry of the graph, if I plug negative x in for x in the function, I see that I end up with the exact same thing as my original function. So if you remember from the previous slide, that means we have y-axis symmetry. This function is not a trig function, so we don't have to worry about periodicity. Furthermore, because it's a polynomial, we have no discontinuities. To find horizontal asymptotes, we take the limit as x goes to infinity, but in this case we end up with infinity. And by symmetry, if it goes to infinity as x goes to positive infinity, then it should also go to infinity as x goes to negative infinity. The other way that we could do this, though, is actually to evaluate the limit as x goes to negative infinity. In either case, we see that we have no horizontal asymptotes. Next, we want to look at intervals of increase and decrease. So we evaluate the first derivative, find the critical values of it, and then plot them on the number line. We now plug in values in each interval into the derivative to see whether the function is increasing or decreasing on each of those intervals. From this, we can find relative mins and relative maxes. We then need to find the minimum values and the maximum values. To do this, we plug the relative maxes and mins into the original function. By symmetry, since we've plugged in f of negative square root of 2, we know that f of negative square root of 2 should equal the same thing as f of square root of 2. So this actually saves us some time. This is why we want to solve for the symmetry at the beginning of the problem. We can also find the max value by plugging in 0 into the original function. And finally, we can find the concavity of the function by taking the derivative of the first derivative, so in other words, the second derivative, and finding the critical values of it, and plotting those out to see when our function is concave up and when the function is concave down. We therefore have inflection points at f of negative square root of 2/3, and then due to symmetry, we also will have an inflection point at the square root of 2/3, comma, negative 130/9. Now there was a lot of math going on this slide. Let's try to put this all together and try to graph the function. Alright, so remember that the function f of x equals 2x to the 4 minus 8x squared minus 10. I'm just going to summarize everything that we found on the previous slide. The x-intercepts were at plus or minus the square root of 5, 0. The y-intercept was at 0, negative 10. And we have y-axis symmetry. We saw that the function was continuous and had no discontinuities. Furthermore, we had no horizontal asymptotes. We also saw intervals of increase and decrease, giving us a relative min at negative 2 and at negative square root of 2 and at square root of 2, and a relative max at 0. We found the y values at negative square root of 2 and 2 to be negative 18, and the y value at 0 to be negative 10. For concavity, we saw that we had inflection points at negative square root of 2/3 and positive square root of 2/3, comma, negative 130/9. We're finally ready to graph the function. Here I've drawn my x and y axes, and I'm going to start by plotting all the important points that we've seen. So plus or minus the square root of 5, plus or minus the square root of 5, 0, 0, negative 10. And then here you see negative square root of 2, negative 18, and positive square root of 2, negative 18. And also negative square root of 2/3, negative 130/9, and positive square root of 2/3, negative 130/9. So now I've plotted all the important points of my function. Now I just have to connect the dots in a way that satisfies my y-axis symmetry, no horizontal asymptotes, and the increase and decrease and concavity. When we do this, we see that the function needs to be decreasing until we get to the relative min. Then it's going to increase until we get to the relative max. Then it decreases again to the relative min, and then it increases forever. Furthermore, we see that the function is smiling until we get to negative square root of 2/3. Then it frowns until we get to positive square root of 2/3. And then it smiles again forever. So although this is a sketch, it's actually a very good approximation of the graph of f of x equals 2x to the 4 minus 8x squared minus 10. Although this was long, notice that it was not too hard. The more you practice, the better you're going to get at this. Let's try a function where I actually give you all the information about the function and ask you to just draw the graph. So sketch the function where the x-intercepts are at plus or minus 1, the y-intercept is at y equals 2, we have y-axis symmetry, vertical asymptotes at x equals plus or minus 2, a horizontal asymptote at y equals negative 1, and the increasing and decreasing intervals and the concavity are as follows. I'm going to start by plotting the interesting points. First with my x-intercepts and y-intercepts. So we see that our x-intercepts are at plus or minus 1 and my y-intercept is at 2. Now I'm going to plot draw my asymptotes. So I have vertical asymptotes at plus or minus 2 and I have a horizontal asymptote at y equals negative 1. And now I need to connect the dots in a way that satisfies my slopes and my concavity. So I want my graph to be decreasing everywhere below negative 2 and increasing everywhere below 0, decreasing above 0, and here we see it's concave down as well. And then in order to have my function be decreasing and concave down below negative 2, it has to arch down like that. And due to y-axis symmetry, we know that we'll have the same exact thing on the other side. So this is the graph of this mystery function.